Hello, myself Ashwin, and I will discuss about quantum error correction. So, what is error correction? Error correction is the science of encoding the information so that after the error taken place, it is possible to recover the original information. It is like finding two functions C and D so that we can encode our information using E and we can decode it using D. So, why we can't use classical error correction in quantum? So, there are four reasons. No-cloning theorem, which forbids the copying of an arbitrary state without disturbing the original. Like we can't do measurement, otherwise our superposition state will be destroyed or collapsed. And the another thing is continuous errors on the state and phases, which are possible only in quantum, not in classical case. So, how to implement error correction in quantum? So, the way to encode a qubit alpha 0 plus beta 1 is to encode it as alpha 000 plus beta 111. And while doing this encoding, we have repeated state only in computational base. Superposition states are spread out but not copied or repeated. And we can use the same thing, like measure all three qubits and see which one differs from the other, and using the majority we can flip the wrong qubit back. But like in this process we are doing measurement which we don't want. So how to avoid this? So we can use error syndromes, or we can use two anislas and performing operations will be controlled by qubits 1 and 2 for the first anisla and 2 and 3 for the second anisla. Like these anislas will give us answer to the question whether first and second qubit are the same and whether second and third qubit are the same or not. And we can use these error syndromes and some correction logic to correct our bit flip error. How can we correct discrete phase flip error? It is actually same as the bit flip error, but in the different basis, like plus minus basis. It is same as the bit flip error, and we can correct this also using the same logic, but we have to use the Hadamard gate while correcting this error, because this gate actually changes the basis. So now comes the continuous phase flip error, which can be represented by this matrix R theta. It is like applying this matrix on our original qubit. After doing the measurement on the error syndrome, we will get the state. We will get our original state back with the probability cos theta by 2 magnitude square, and similarly can get our original state fluid with probability sin theta by 2 magnitude square. Basically, these two qubits represent the error syndromes for the identity error for the phase error on qubit J. All these development lead to quantum error correcting code, which is a 9-qubit code in which 0 is encoded as this and 1 is encoded as this. And by using this encoded, we can able to correct any flip error, phase error, and both at the same time on the same qubit. It is like correcting error due to X, Y, and Z. So now we are going to the very important theorem, which is which says QECC, like quantum error correcting code, can correct any unitary operation on a single qubit. Like if QECC corrects error E and F, which are basically any unitary operation, then this QECC can also correct any real combination of these unitary operations for all A, B. Therefore, if we apply this linear combination on our state and encode the state, we will get psi times alpha. This is qubit of error syndrome, and beta times this is another qubit of error syndrome. And if we measure this error syndrome, we can recover the original state. So this is from my side. Thank you.